Hello, everybody. This is Gene Bohensky, the Director of Application and Partner Learning at Perma. And the title of this webinar today is Adding Humidity to Gas Streams with Permapure's Nafion Tubing Humidifiers. And just to get started with some housekeeping items, we will have ample time at the end of the presentation to answer any of your questions. You will be able to unmute yourself at the end and just say your question, or you can also write your question in a chat box during the presentation, and we'll come to it later on at the end. So let's get started. For over 40 years, Permapure's Nafion tubing humidifiers have been used for a wide range of applications to humidify gas streams in medical, fuel cell, industrial, and scientific applications. Permapure is the world's only manufacturer of Nafion tubing. In this presentation, we will present an introduction to Nafion tubing humidifiers, learn how to size them for your applications, and discuss their main uses. But let's review the basics of humidity and dew point first, just to get our minds ready for some concepts that are going to be presented in the presentation. We'll start with relative humidity. So relative humidity is the amount of water vapor present in the air expressed as a percentage of the amount needed for saturation at the same temperature, or the amount the air can hold. The relative humidity represents how close the air is to saturation. It cannot be represented by a measured value, as the amount changes with temperature. So saturated air will have a relative humidity of 100%. For example, you need the relative humidity of 100% to have rain form in clouds or water to condense. And relative humidity is the term weather forecasters use when we're talking about weather. We're talking about how the air feels. It's usually in terms of relative humidity. So let's go to dew point. The dew point is the temperature of the air which is needed for condensation or dew at that particular temperature. So that is expressed really as a temperature, and that's connected to the amount of water in the air. If you take a glass of ice water and it develops condensation on the glass surface, the air on the glass is cooled to its dew point and the water vapor has condensed and created dew. The dew point can be used to calculate how much water vapor is in the air and can be represented by either a value in parts per million or as a pressure. That is, if you take a constant, use the constant standard reference of the atmospheric pressure, then the dew point is directly related to absolute humidity. And in Permapure's performance charts for our dryers, we typically look at dew point as well as our humidifiers. We talk about the dew point that we're able to achieve, because the dew point is an actual value. It's a number that can be used in a calculation. So let's look at the relationship between relative humidity and dew point. In this slide, we show, for this example, how the capacity of air to hold water increases as the air is warmed and decreases as it is cooled. So there at 55 degrees F, which is roughly 15 degrees C, you can see the cylinder is pretty short. And at 80 degrees F, that's 25 degrees C roughly, your capacity is over double. For the example, let's show an amount of water that doesn't change over the temperature increase. And let's then overlay the two in the next slide. And this visualizes the concept of relative humidity, where your absolute humidity is really the same on all of the temperatures, but you could see the relative humidity at 55 degrees or 15 degrees C is 100%, but at 80 degrees Fahrenheit or 25 degrees C, it's down to 42%. So as a review of relative humidity, given a constant moisture content or dew point in the air, as temperature rises, relative humidity falls, and as temperature falls, relative humidity rises. So the next slide shows how the dew point in the atmosphere varies over a year. This has profound implications for any of us that are doing measurements of ambient air or ambient conditions, or we want to humidify a gas stream with one of our Nafion tubes exposed to the atmosphere, which is what we do, or dry as a gas stream when exposed to the atmosphere. You could see that during the warm summer months in the middle of the year, the average dew point is higher, but there is also a great variation from day to day and to week. And here, this goes to show you that if you're making measurements, you have this effect of water present that can have profound changes on your measurements. So let's look at the relationship between the dew point and relative humidity and how they vary over 24 hours. This is a relationship that changes day in and day out. At the bottom there, the blue line represents the dew point temperature. That's the actual amount of water in the air. That doesn't really change too much. And then you see the red being the temperature of the air and the green, the corresponding relative humidity. They rise and fall in inverse with each other. So as the temperature rises, your relative humidity falls. And as your temperature falls, your relative humidity rises. What's interesting is that you have in the early morning, when you get dew falling everywhere, that's when you actually have water condensing out of the atmosphere. That water gets everywhere. And of course, that wreaks havoc if you're doing any type of environmental measurements. So whether you're humidifying or you're drying, these have profound implications on your measurements. So let's look at a review of sample gas humidity. The dew point is the temperature at which the air is fully saturated for a given amount of water, or the temperature at which condensation just starts to appear. Relative humidity is the ratio of the amount of water in the air compared with the fully saturated amount. And the absolute humidity is the absolute amount, or the amount of water given in a volume of air. And as I've mentioned before, if we are using the atmospheric pressure as a baseline, then the absolute humidity and the dew point is directly related. So let's talk about Nafion polymer. What is Nafion? So Nafion has become such a valuable material for industry and has so many unique attributes. And PermaPure harnesses just one of the main attributes, which is the water transfer properties of the material. So Nafion is a copolymer of Teflon and sulfonic acid, and it's highly resistant to chemical attack. So it has a very similar chemical resistance property list, just like Teflon. Nafion polymer removes water by a first-order kinetic reaction, so equilibrium is reached very quickly between the sides of the membrane, typically within milliseconds. So the transfer of moisture is driven by the differential water vapor pressure between the membrane sides. And this Nafion polymer permeation selectivity is based on the chemical reactivity of water with the Nafion, not the size of the molecule. So it is not traditional permeation. So with traditional permeation, you can look at it like a bug screen, where you have a screen with holes in it, and the holes are sized to let certain elements through, or certain components through, molecules, for example, and leave the other ones out. That's not what Nafion is. Nafion is different in that the water actually becomes part of the material's chemical structure and moves through its lattice from one side of the membrane to the other based upon this differential vapor pressure of water. And here on the right, you can see a representation of a Nafion tube with the flow moving from the right to the left. Actually, for humidification purposes, we're going to do it the opposite way. We're going to flow from the left to the right. So you're going to see your sample that you want to be humidified, or your gas stream you want to be humidified, is represented by the red, green, and yellow jelly beans, and it is moving in. They're moving into the Nafion tube, and there you have the blue spheres putting water into that gas stream based upon the vapor pressure differential and humidifying the gas stream. Another thing that is very unique about Nafion is this process is very selective. That means only water vapor goes through in this way, and a lot of the other components that we don't want to pass through when we humidify gas streams don't, including CO2 or oxygen, other components that are in solution with the water. So PermaPure humidifiers have two main operating modes, and they operate differently. And we're going to be discussing each operating mode separately. The first operating mode is going to be the gas-to-gas operating mode. That's when we are humidifying in the gas phase, when we're taking water vapor, and that water vapor is going to humidify a gas stream inside the tube. The second mode is water-to-gas mode. This is where we take liquid water and we saturate the membrane with liquid water, and then we pass a gas either through the inside of the tube when the liquid is on the outside of the tube, or we can pass the gas on the outside of the tube when the liquid is inside of the tube. These are two different operating modes, and they behave very differently and have different effects on humidification, which is why we want to talk about them separately. They have different performance and different implications for the usage of the humidifier. So let's look at the first mode, which is water transfer in the vapor phase. So in the vapor phase, water or other polar chemicals can be transferred, and in this phase, no energy is required. It is strictly driven by the differential vapor pressure between the membrane sides. No liquid water is present to affect chemicals soluble in the water. There are no moving parts, and it's scalable. So let's take a look at our first product that uses this principle, which is our BE series, our braided exchanger. This is where we have braided Nafion tubing that is exposed to the atmosphere. So what's interesting about Nafion is the tubing is very difficult to connect anything to, because you can't really glue anything to the surface of Nafion, and it doesn't really stick to anything. So we developed a method at PermaPure using a weaved polypropylene braiding. What we do is we weave the braiding along the entire length of the tube. That braiding gives us some mechanical strength. It also allows us to distribute the forces when we are coiling the tube so it doesn't kink. And I guess the most important thing about the braiding is it allows us to connectorize the material. What we do is we injection mold a polypropylene end in various types of sizes and shapes and connectors. Connector designs, but basically the concept is that we're taking the polypropylene and we are encapsulating the polypropylene netting, and what that does is provide a very strong strain relief, where we provide a plastic attachment where we can attach a connector, as shown on the picture there at the right. We can attach a metal connector, a typical compression style connector, and we have a very strong strain relief. That means we can pull that connector, and the mechanical strength is from the encapsulation or the enveloping of that polypropylene around the netting that has been weaved around the tube. So what this allows us to do is expose the Nafion to the atmosphere. When we're humidifying with the atmosphere, the ultimate performance is a function of the dew point of the atmosphere where the unit is operating. That means the amount of humidity that you can get into the tubing, into the sample, is going to be based upon the amount of humidity in the atmospheric air. Now, if you remember those graphs that I showed you about how the dew point changes throughout the year, this is important to understand, because when you do this, you will have a variable result as the amount of moisture changes in the air. So this is often used to equalize humidity of a gas stream with the sample gas. The product is available in a variety of lengths and tubing diameters, and we have flow rates to 2 liters per minute and pressures up to 255 psi, 17 bar in the tube when dry. So here's a very common application for these, which is calibration gas humidification for analyzers or gas detection. There you see a calibration gas in a bottle there with a regulator and a flow meter. And then before we go to the analyzer, or when we want to calibrate a gas detection system, we put the Nafion tube humidifier in line, and it extracts the moisture from the outside air and humidifies the gas stream. And here we have some humidification performance charts for this. It's the first time we've published them, which gives you two conditions that show you how well these products can humidify. So on the left, we're looking at the humidification in ambient conditions of 20 degrees C with a 15-degree dew point, which equates to a 73% relative humidity. And here you can see that as you increase your length of your humidifier, these are the performances that you can get with a 24-inch BE series, BE110, and a flow rate of 1 liter per minute. You will reach a relative humidity of roughly 55% in the environment where outside you have 73% relative humidity. On the graph to the right, we have a similar curve that's been done in ambient conditions of 35 degrees C with a 27 degree dew point, and that's at a 63% relative humidity. And you could see that, let's look at this 24-inch again at 1 liter a minute. You're also down to 45% relative humidity from starting out at a 63%. So it is very efficient, and it shows you you can capture a lot of that humidification from the outside air can be brought into a gas stream using a BE. So let's look at tube and shell Nafion tubing humidifiers. These work just like our dryers. You've probably seen this before in our previous presentations, but I want to point out that we're looking at water and we're looking at humidification. With this type of humidifier, you're putting the dry gas in through the center of the tube there in a dark blue, and your wet gas is coming in the opposite direction from the right to the left, and that's coming in white and turning light blue, leaving out to the left. So what we're doing is it's similar to a dryer. Your dry gas is flowing inside, and in this case, the flows are sealed off for each other. And we have two products that can be used in this method. Those are our FC series multi-tube or MD series single tube. Yes, those are the same as the dryers, and you can use them for humidification in the gas-to-gas mode only. We don't have performance curves for this. However, the performance of the MD series will be very similar to the BE series. And a lot of researchers use these for small quantities when they're humidifying aerosol streams is a common application, especially for the FC series. So with our FC series humidifiers, these were primarily designed for fuel cell applications, but they're used in many other applications. And they're designed for gas-to-gas humidification. We can achieve a high degree of water transfer, up to 85% of the water content in the gas-to-gas mode. In the gas-to-gas mode, no energy is required. It is highly reliable, and there's a wide range of sizes available for flows up to 4,000 liters per minute. So here is a fuel cell application where we are humidifying with recycled exhaust gas off the fuel cell stack. So what we're doing is we're bringing in dry air on the left that's coming into the humidifier. It's being humidified by the wet exhaust coming off the fuel cell stack. From there, the wet air is going back into the fuel cell stack to improve the efficiency of fuel cell operations. And then again, the hot and wet gas is coming off the fuel cell and is being used for humidification. This is a classic way that our humidifiers are used in fuel cells. So in the application, the benefits for Perma-Pure humidifiers is, first of all, they are very highly efficient. There's no power consumption, no freeze-thaw issues, and there's a self-limiting humidification. The performance is strictly dependent on the amount of Nafion present in the humidifier. And here's our FC gas-to-gas performance chart, and I'm going to spend some time to explain how to use this chart because it is very confusing. It took me a while to understand the chart, but once you do, it's fairly simple. So on the left is your temperature in dew point, it's your temperature in dew point or actual temperature. We call that the approach temperature or approach dew point. And on the x-axis are your flows of your different humidifier sizes. Because all Perma-Pure humidifiers really perform the same, because the performance is strictly dependent on the amount of Nafion in the material, we can make one chart for all of the products and just change the numbers. So let's look at what the graph means. We have two curves there. The pink curve is the approach dew point, and the blue curve is the approach temperature. Now, what do we mean by approach temperature, approach dew point? Well, in short, what this means is it is looking at the difference in the dew point or the temperature between the gas that is being used to humidify the gas stream. Okay, that's your source humidity gas stream, and the resultant humidified gas, so your result gas stream or your resultant gas stream. And so these numbers represent the difference. Okay, so for example, let's take a look at right in the center there, our FC 600-14, and at a flow rate of 2940, our approach temperature is roughly 3.8 degrees, and our approach dew point is roughly 7.5 degrees. That means if our gas stream used for humidification, our source gas stream, is 60 degrees centigrade, that means that the resultant gas stream coming out of the humidifier is going to be 60 minus that 3.8, or 57 or 56.2, right? That's what, because we're looking at the difference between the two. Similarly, by the dew point, if our dew point was 50 degrees C and our approach dew point is 7.5, then our resultant dew point of the gas stream coming out of the humidifier will be 50 minus 7.5, or 42.5 degrees C. You understand? So this is this graph is a relational graph that shows the relationship between the gas, the source gas being used for humidification, and the resultant gas exiting the humidifier. Okay? So let's review these again because it is confusing. The approach dew point is the difference in the dew point between the recycled gas used for humidification in a fuel cell, that is the cathode exhaust inlet, and the resultant humidified outlet gas. And the approach temperature is the difference in the temperature between the recycled gas used for humidification and the resultant humidified outlet gas. So let's go through another calculation just to bring this point home. So the approach dew point is dP1 minus dP2. Your temperature is T1 minus T2. dP1 and T1, meaning the dew point, the temperature of the gas being used for humidification. And dP2 and T2, meaning the resultant outlet gas. So our example shows here on the screen a humidifier inlet of 70 degrees cathode exhaust with an approach dew point of 4 degrees C and an approach temperature of 2.5 degrees C. That yields a humidifier outlet of 66 degrees of a dew point, that's 4 degrees difference, at a 67.5 degree temperature, and we can calculate that relative humidity, which is calculated at the 67.5, right? Not at the 70 degrees C. And that relative humidity is 93%. So let's look at some humidifying applications and get for gas to gas. So number one, sample gas conditioning to equate humidity, A/B testing with calibrated gas. There's some analyzers that have this built in. Gas conditioning to add humidity. There's a number of manufacturing processes that we support with humidifiers that add humidity to gas streams. We humidify calibration gas and particularly for gas detection sensors for higher accuracy and less false alarms on gas detection. For aerosol and particle analysis, we maintain the relative humidity for consistent measurements during the daily relative humidity cycle. It's also being used in extremely dry environments to get a good baseline, because you need to get the relative humidity of particle streams in the 30 to 40% range to get accurate results. And relative humidity experiments maintaining baseline measurements, and of course for fuel cells, for fuel cell humidification. So let's go now to humidifier operating mode 2, which is water transfer in the liquid phase. So this is a little bit different than the gas phase, because here liquid water is transported through the Nafion membrane in the liquid form and is evaporated on the outside surface. So this is very interesting in that what's going through the membrane is actually liquid water. That transfer rate is faster than gas to gas. In fact, we've estimated that to be roughly 3.5 times faster. So you can get the highest performance, the highest amount of water transfer into a gas stream with water to gas. And you can see with our performance curves that the flow rates that we're able to get with using water to gas transfer are much higher than gas to gas. So we're putting a lot more water into the air, and the capacity grows greatly. We can achieve a high degree of humidity, up to 99% relative humidity. And the vaporization is selective. No other chemicals in the solution with water will pass through the membrane. So for example, humidification of chambers where oxygen needs to be kept to a minimum. This is important because with water, there's always a certain level of oxygen that is dissolved into the water, which is, of course, how fish survive, because they can use and get that oxygen out of the water and breathe. So this is very important to understand that this is very selective and very high transfer rates. But there's a couple of caveats here. First of all, the water must be heated to restore energy used in evaporation. So it's not energy free. You need to continuously heat the water, because the evaporation is going to chill the water left behind. You also need to use deionized water, as ions in the water will reduce the performance. What happens is that particularly metal ions are attracted to the same channels or the same surface area as water, and will block the water transfer channels through the material. And you have to circulate the water to maintain consistent performance. Pressure drop may be a limiting factor as flow rates rise through the tubing. The other limitation is that there's a pressure limitation of the tubing when saturated with water, as the tubing becomes soft. And water-soluble compounds may dissolve into liquid water droplets on the inside of the tube surface. And that was an important concept, because what happens is that you have water droplets on the outside of the tube where your gas is. And we found in one instance with a company that was trying to humidify a calibration gas stream with SO2, that when using a water to gas humidifier, they were getting SO2 losses. And what they were finding is that the trace amounts of SO2 in the calibration gas were actually being dissolved by the miniature water droplets the micro water droplets on the inside of the tubing. We only recently discovered this, and it's something we want to point out in case people are looking to make measurements. So let's look at our MH series single tube humidifier. This is a simple tube and shell design using DI liquid water. It's also available in a wide range of lengths and tubing diameters with materials in polypropylene, fluorocarbon, and stainless steel. Flow rates to 20 liters per minute and pressures to 15 psi, 1 bar in the tube when wet. And here you could see a similar diagram to our MD, except we have the sample gas going through the inside of the tube and your water going on the outside of the tube. Sometimes we do that in the opposite way, where we have the water in the inside of the tube and the gas going on the outside of the tube. They both work. One thing you have to understand is that even though it looks just like an MD, it's not an MD, because when Nafion is saturated with liquid water, the dimensions of the material change. It expands 15% in length and in outside diameter. So what happens is that when we build these humidifiers, we have to build them with the tubing already saturated with water, because what would happen is if we use the standard MD and you put water in it, the tubing will try to expand and it will kink because there's really nowhere for it to expand in the shell. So it's very important to understand that is why we have a separate product line for the MH. It's also important if you're using an MH that you never want to let it get dried out. It always has to be stored with water in it. Otherwise, the tubing will shrink and it will pull outside of the ends, and you will have to recondition the tubing in order to get it to be used again. Or you might not be able to use it again, depending on how what the condition is after that. So it's important to understand why it's a separate product line and that there's a separate production process for it. So again, the operating mode is water to gas only due to the expansion of the Nafion tubing when saturated. It continuously humidifies. It has a fast response time. It's self-regulating, no moving parts, and excellent corrosion resistance. Here's humidifying with a liquid water reservoir. This is one way to humidify. I don't really think this is the best way. This is where you have the water in a reservoir that is feeding the humidifier tube, and in this case you have to heat the shell in order to keep the water at the same temperature. I don't think this has the best performance because you don't get, it's not always as consistent. What I like better is humidifying with circulating water, where you're heating the water and you're circulating this water fast enough. I think the rate is something like 1/10 to 1/4 of the flow of the gas stream. You have to circulate the water through the humidifier, and here in this case the water is going through the inside of through the outside of the tube and inside of the tube, and your sample inlet is on the outside of the tube. This gives you the best performance. And let me explain to you what happens if you don't heat it properly. What happens is that you might get cold spots in your humidifier, and there you'll have issues because you have erratic performance. In some cases, if you don't heat enough, you can actually cause that area in the center of the humidifier to freeze. And this is because evaporation takes so much energy. So you have to make sure you put in the energy that will be required to vaporize the water, because that's the principle that this is using to humidify a gas stream when going from water to gas. So here's an MH performance curve. You could see the performance is at 4 different water temperatures. Let's just take a look at the 12-inch humidifier at 3 liters per minute. We could see that using in the pink, we have a 30 degrees C water. we can get to a dew point of roughly 26. With a 50-degree water, we can get to roughly 37. And with a 70-degree water, we can get to roughly 52 degrees dew point, okay? You can see how the effect of the water temperature can change the performance. Of course, this all depends on the amount of heat energy that you're putting into the water to keep that water temperature where you need it to be. Depending on what you're doing, you can control the humidity with water temperature, but really what we've figured out in our own labs is how to control the temperature with pressure. And in a future presentation, we're going to go over our new humidity generator that uses pressure as a principle of being able to regulate the amount of humidity coming into the gas stream. So our BE series can be submerged in water for certain applications. Performance curves are similar to the MH series for the equivalent length and tubing diameter. In some cases, people have used the BE, and there is an expansion issue as well there, but some people have cut the braids to allow the Nafion tubing to expand. This is okay as long as you understand what you're doing, but we've seen some customers do this because it helped in their applications. FC humidifiers can also be used in water to gas applications and can achieve a high degree of water transfer, up to 99% relative humidity. We have a wide range of sizes available for flows up to 15,000 liters per minute. And you have to watch differential pressure on tubing, as the maximum is 5 psi, 1/3 of a bar, due to the tubing diameter. It's very thin and small tubes in these FCs for efficiency. And here's your water to gas performance chart that looked very similar to the MH. It's based on the same concept. Here, let's look at our top line, our FC 600 8-inch. Let's look at 5,000 liters per minute there. That's the third number over. You could see with an 80-degree water, you can get to a dew point of roughly 64. So let's look at some humidifying applications, water to gas processing and manufacturing processes, oxygen for breathing, for comfort. We have some extensive experience with some applications there. For fuel cells, controlled humidification of chambers. And again, the limitation is that liquid water droplets on the inside of the tubing might interfere with the sample gas chemicals or particles, which could require a dual stage humidification system. So here you'd use the first humidifier using water to gas to make the humidified air or the transport gas for the main application. And then the second humidifier uses the humidified air transport gas to condition the main gas. We have our 10 questions that we ask customers in response to providing application information. Basically, what we want to know from the customers, all of the related information on the application so that we could make a good assessment.